Hello, thank you. I hope you're all wide awake, much more than I am after last night's very nice party for all the speakers. Who went to the talk just before this one in this room? Okay, you've probably seen half of my talk already, because the speaker very kindly, thank you very much, covered a lot of the stuff that I'm going to cover, so I'm going to change it slightly and do some more code, show you some more code. I might do a little bit of live coding, but it's mainly kind of showing the code and evaluating Clojure, so you get some kind of experience. What you'll quickly see is the biggest kind of blocker that people have to getting into Clojure is actually just what's seemingly a very strange syntax of the language. But actually, I'm sure you'll come to love it as much as I do by the end of my talk. That's what my aim is anyway. Has anybody done any Clojure before? A few people, okay. Has anybody done any Lisp before? Oh, I could be in trouble. Okay. And who's done Scala and things like that? Oh, not so many. Oh, you got your work cut out there. And anybody done any Haskell? Oh, some hardcore people. Excellent. Yes. Unfortunately, there's not going to be any types in Clojure. Well, there are types underneath, obviously, because we're running on Java. But yes, it's a very dynamic language, so it's very different approach to Haskell, even though there's a lot of common aspects as well. So let's get going. Just before I jump in, just to introduce myself very briefly. So my name is John Stevenson. I'm on Twitter, and I'm part of the London Java community as well. So we've got about 6,000 people signed up for the London Java community now, so it's a really active Java community, and it encouraged me to get into speaking and organizing events, and it's been a real kind of boost to my career. So it's been really great fun, and we do lots of stuff. We're even working on things like the OpenJDK and helping shape the future of Java with OpenJDK 9. And I've got a website as well, which I blog on Clojure and all sorts of things like that. So, what is Clojure? That's a very good question. Hopefully that's the question you're all asking yourselves. So it's a functional language, as again the previous talk was touching on. Functional language, very different to OO. So this is probably the biggest challenge you'll really have in actually adopting things like fully adopting Scala and adopting Clojure or Haskell. It's not that functional programming is difficult. It's just you spent your time learning object-oriented way of doing things, and it's very different from doing the functional side of things. You still get things like a little bit of encapsulation, but you don't have huge inheritance trees. You're not like doing this huge inheritance design. You're not doing a lot of huge kind of object-oriented design in your functional programming. It's more like going back to Lego and taking little Lego pieces and putting them together. It's lots of little functions that work together. If you've ever used the Unix operating system, Linux, it's very much like that. You've got all these little commands that you can kind of assemble together that do so much more powerful things when they combine together. So it is quite a shift to get started with it, but I think you'll learn an awful lot from it. Even if you don't do functional programming as your day job, there's a lot of things you can bring into Java that you do every day, like making everything final by default is always a good start. That helps you kind of manage state, and that's one of the other aspects of functional programming we'll get into as well. So Clojure runs on Java, on the JVM. It also runs on JavaScript. You can run it on Nashorn as well. You can also compile it for ClojureScript. You can use ClojureScript to compile to JavaScript, and you can even compile onto the Microsoft Common Language Runtime as well. So it is quite flexible where you can deploy it from. So it's a hosted language, so it was never designed to be just by itself. It's always been designed to run on top of something else. And so we can use all the really good experience that's gone into the JVM and leverage all that. And it's a modern Lisp. So some people look at Lisp and they think, oh, it's just all brackets, it's horrible. And there's possibly a case for that. The way you format Lisp and the way you build Lisp up, it does look a little bit confusing. So some of the slightly more archaic things in Lisp have been modernized. And again, we're hosting this on Java, so you've got a modern runtime to actually do it on. And there's tons of companies and stuff that are actually using Clojure now. There's lots of things from big data, financial institutes, and even creating games and playing music as well. There's quite a few bands that actually use Clojure to live generate music and video content. So they're actually playing concerts with their laptops. It's quite fun. So what's the motivation for Clojure? Well, Java's evolving, not quite as fast as some people would like. Hence the reason why there's Scala and Clojure and Jascal and JRuby. So the JVM is amazingly rich, but Java has been a bit more traditional and quite conservative. It's starting to change. You're starting to get a few extra bits in there, which is, if you're busy and you don't have time to learn all these things, is great. But if you want to use lots more features, then it's usually easier to jump to a different language. And Clojure takes a very different approach to Scala. Scala has lots of amazing kind of technology and tools and concepts inside it. It's a very big language. You've got all the things you can do in Java, and then all the functional stuff. So it's a multi-paradigm language, where Clojure is much simpler. It's really focusing on the functional aspect, the immutable aspect of building applications. And it takes big problems and encourages you to break them down into small pieces, like microservices, for example. It's very easy to build a microservices system in Clojure, and a lot of our software is basically just lots of small, really specific libraries that do some amazing things. And again, from the previous talk, scaling is one of the biggest motivating factors now. So our processors aren't getting any faster. They usually tap to about 3 gigahertz like cycle speed. So the way you get more processing power in your laptop is by having more cores. So if you've got a Mac, you've got 4 cores in it. I'm sure within a couple of years that'll be 8 cores, and then in 5 years' time it'll be like 128 cores. Won't be too far away. I mean, I think there's more cores in my phone than there is in my laptop, which is bizarre. But it makes it work, and that's the way that the hardware people are scaling up. So to take advantage of that, functional programming is really good. And there's a big focus on immutability as well. So actually having mutable state is just crazy and painful and difficult, especially when you start scaling up. If you're at Facebook scale or Twitter scale, actually having mutable state and trying to manage lots of changes, you're just like locking everything over and over again, or you're overwriting things and having all sorts of weird and wonderful side effects. So it really isn't, it's really not the kind of thing you want to do. And it can lead to some very, very painful times when you're a developer as well. Who does concurrency in Java at the moment? Who likes doing concurrency in Java at the moment? A couple of people. Good for you, yes. It's good to have a good challenge. Keeps you awake. And probably good for your career as well. But it doesn't have to be like that. So Clojure is very simple. So let's have a look at some Clojure. So hopefully you'll be able to read this very quickly. So the first line in yellow is defining a namespace. It's just like a package in Java. So in Java, you've got all, like packaging structure to give you different areas of functionality. So it's the same thing with Clojure. Next line, def my data. So we're just basically giving a name to a piece of data. So we're binding a name and saying we can use this name to refer to that bit of information. And then we're defining a function called doStuff, which is not a very exciting function. We can give it parameters, and then we can use those parameters to do some behavior. In this case, we're just going to print out. I didn't switch on. We're just going to print out, so you string to print out the parameter value. And so we actually call this, so this is the function that we've defined, and we actually call that function by putting it in a list. So this is where you get the evil brackets all over the place. So actually, if you took this list, if you took this bracket and put it at the end of this data and put a parameter in there, ooh, that looks like Java. So it's not actually a huge amount of difference. It's just we're just shifting things a little bit, and there's no semicolons anywhere, except in comments. So that's where we use semicolons. So it's quite nice. So if you can understand that and read that, then that's a lot of the syntax that you'll use for the first week of doing Clojure. There's other things like, then it's just a matter of learning all the functions that come with Clojure. And so it's a very data-driven language. So you're defining these data structures that describe the information you're going to be working with, and then you define behaviors which will act on those data structures. And so a common quote that we talk about is that it's better to have 100 functions acting on like a single data structure than it is to have like lots of different data structures and lots of different functions going here and everywhere, which is kind of what Java does. So Java has lots of different classes, where each class has its own data structure, and classes call each other and play around with each other's getters and setters. This is why you have private and public and protected, and then your friends can play with your privates. It's all a bit weird, and it can be very confusing. You do some very powerful stuff, but then it is your responsibility to kind of keep all that in your head. And when you're working in a big team, that can get quite a lot to remember. So the nice thing about Clojure is it's got built-in data structures. So there's lists, maps, vectors, and sets. Is it my phone? And so these are really nice because they're immutable, and you can mix them around a little bit as well. So you can create really complex data structures that are still quite readable, because essentially your data structures are code. So you can actually just show, you can read the code, and it's your data structure, and it's all the same syntax. So in here we've got basically, we defined a map, which is just a key-value pair. And so we've got a keyword, which is a key, value 1, which is a value. We've got vector with a vector, map with a map. So we can mix all these different structures together and come up with something. So I've got some examples later on. I'll show you, to give you an idea how it does. Here we've got another example where we're defining locations, and London has a location. So this is a map, and it's got a keyword of London, and the value is actually another map, which is another set of keywords and values. So London has a location of latitude 34, longitude 57. I mean, that's kind of readable. Even if you didn't know Clojure, you could read that quite easily and understand what it was. You might not be sure about def, but you can say, oh, locations, London, and so on. It's very easy to just read Clojure. And most Clojure is written fairly well, fairly readable as well. Oops. Yeah. And that's it. That's actually Clojure. That's the core of Clojure. These are all the primitives that make up Clojure. If you actually take one off the top of the list there, that's actually Lisp. Lisp actually has even less. So there's only like 8 things that ever made up, 7 things that made up Lisp. They added one for Clojure, and then the 4 at the bottom for Java Interop. So the entire language of Clojure is built from these building blocks. Everything else is something called a macro or a function. And a macro is just an amazingly powerful way to extend the language, which we'll have a look at later on. And there's all the usual data types. So there are types in Clojure, but you just don't need to define them. Clojure will work them out itself. And we look at status approach and persistent data structures. So all the lists and vectors and maps and sets are all immutable. So when you create them, you can't change them. So there is one immutable data structure in Java. Do we know what that is? String. Yes. I don't have any prizes to give out, sorry. Only my thanks. But yeah, so it's like having, if everything was like string. You actually can't create, you can't change it once you've created it, which you would think would be a bit of a problem. But there is a way to handle that. So we've got these persistent data structures. So actually, you can look like you're changing. So you take a vector, which is like an array of numbers of 1, 2, 3, 4, 5, and you add 6 to it. It looks like you've actually changed that vector to just add 6. What you've actually done is you've created a second vector that just has the value 6 in it and points to all the relevant things in the previous vector. So here we've got, it's a bit small on this screen, but we've got a vector, imagine we've got a vector of 0, 1, 2, 3, and then we add, 0, 1, 2, 3, 4, 5, 6, and we add this 7 to it, 6 and 7 to it, and then, so that creates a second copy of the vector, and then we have a third vector where we add 7, 8, 9, and 10. And so what we're actually doing is sharing memory. So we're actually able to change or give the appearance of changing values, but still have this immutable state. So we end up having, in this case, three versions of a vector. But if we're referencing the first one, we still see only the first one. We're not affected by anything else. So if we have one function or one thread that's working on some data and changes it, or seems to appear to change it, it's not actually affecting anything else. And this allows us to kind of do massive parallel programming, because we can run our code without any fear that another part of our code is going to interfere with it. So Clojure is kind of based on this mathematical principle of a function. So if you feed in a number into a function, you'll get the same result. So if you always feed in the same number, you'll always get the same result out. So if I feed in hello world as a string into a function that prints out that string, it's always going to do that, no matter what else happens in my program, which is not always the case in other languages. And this is all works in, well, if you do actually want to change state, because if you don't change state, then you're just heating up your CPU and keeping your legs warm. So you can change state, but you do so in what we call a software transactional memory. So it's like having an atomic database in memory that manages all the state changes for you. So imagine what life would be like if you didn't have the garbage collector. Just imagine that for a second. You'd have to do all the memory management yourself. Would that be fun? Maybe for about 5 minutes, and then you wish, no, we want garbage collection back again, because it does so much for you. This is the same thing for, essentially the same thing for state. It's actually managing all your state changes. Underneath it's doing, kind of locking, but ensuring that only one thing is able to update a piece of data at a particular time. And we use a specific function called an atom, or a reference, to mark the fact that this thing is immutable. This piece of data is immutable. And so that way, everything else in our program stays immutable, and just our particular state change that we want to make is controlled. Okay. And one of my favorite things about Clojure is actually working with Clojure itself. It's a very dynamic language in terms of types, but it's also a very dynamic language in terms of the way you program. So normally in Java, you're sitting there, you're writing code, you might write some tests. Who writes tests? Most people. Okay, interesting. And then you compile. You run your tests, you compile, and it takes a few seconds, hopefully not too long. If it's Scala, it might take a little bit longer. But in Clojure, you're actually always compiling. If you're running a REPL, if you're running a runtime environment, when you save something and when you evaluate some Clojure, it's actually compiling to bytecode in the background. So you don't actually have the traditional compile cycle. You just actually evaluate code. So let's actually see if we can show some of that as well. Let's just close this a second. Let's make this bigger. Can we see? Can we read that at the back? Yeah, there's a few. There we go. It's even bigger now. So this is all this code's on GitHub. and I'll show you the link at the end. But essentially, it's just some sample code I've got. I'm using Emacs. You don't have to use Emacs with Clojure. It's not a requirement. It's just an excuse if you want to learn how to use Emacs. But essentially, at the top here, at the top screen, I've got my code. This is the Java. This is the Clojure code, and then at the bottom, I've got what we call a REPL, a read, evaluate, print loop, which is giving me the results of me evaluating the code, but I can also type code in the bottom as well. So I can type in Clojure code. Let's make that a bit bigger. So I can do plus 2, 3, 4, 5, and it gives me the results. So I can instantly, so that's actually compiling in the background. It's actually running straight away. That was quite quick. It's quite nice. Obviously, it wasn't very much code to compile, but it is very, very fast and dynamic, and I could write any Clojure I wanted to in here, any valid Clojure, and I could evaluate it. What we normally do is attach this REPL to our code. So we, in this case, I'm using something called nREPL, which connects my Emacs to my running environment. And I can just evaluate my code here. So I have, and it gives me, so here we're evaluating it, and it's putting in a certain namespace. So this is the fully qualified name for my bit of data I've defined. So I've defined a name called my data for my data, and if I wanted to access it, then it's in the package Clojure through code live demo. So the folder is Clojure through code. The file is called live demo, and the actual name I've defined here is my data. So it's fairly easy to kind of follow that through. It's very simple. It's almost identical to how Java works, essentially, the whole kind of scoping of Java. And so if I want to call that, if I want to see the value, I can just evaluate the name now, and it should give me the actual result. 1, 2, 3, 4 frog. And what's the thing you don't see up there when I define my data? What didn't I actually define? It's the T word. Types. So Clojure just works them out itself. Doesn't need to. I don't need to specify what's a string. It just assumes that frog is a string because it's a fairly safe assumption. If I wanted to check that, I could actually do class. What's my type? And I wonder what type that is going to be. Do we want to know? Guess? No? There we go. So it's a Java lang string. Oh, where did that come from? Oh, look, Java underneath. So it's all Java. We haven't got rid of Java. It's still there. In fact, in every Clojure program, in every Clojure project, when you run the REPL, you've got access to everything that's in Java lang as well already. So you've got Java lang string, date, all the things are already in there. You don't even need to import them into your project. And you can import all the other Java libraries, all the other Java namespaces straight in there and start using them very, very easily. And so what we're doing essentially, what we've done so far is just bind a name to something. So we can do that for a function as well. And we can just evaluate stuff as we go along. So all I'm doing is just asking my tool to basically evaluate line by line so I can get things like Clojure version. Clojure version is just a name that's defined internally in Clojure. It gives you the version of Clojure that we're running. And Clojure is quite small, actually. So when you actually start a new project, which I'll just drop into now, so you would use a tool called Liningen, or Line for short, and you create a new project, and you give it a name. And this basically does the whole Maven thing. So it sets up your default project. There's a whole bunch of templates you can use. So there's a really complex, more involved one for web development called Luminous. This one's just a very simple project. So if we look at Java2days, so it's just got a source tree, it's got a test. In fact, if we go into Java2days, redo tree. Yeah, so that's it. So it's pretty straightforward. You've got like README files, etc., etc. But the interesting stuff is you've got in source, you've got Java2days, which is going to be part of the namespace, cod_test, and core.clj. So all the files end in CLJ. If it's Clojure script, it's CLJS. So my namespace would be Java2days .core, and then whatever functions or names I give to my data structures. So it's pretty straightforward. And if I look in the projects file, oh look, there's no XML. How nice. Because I like Maven, I don't like debugging pom.xml files. So this is actually, what language is this, do you think? It's not a trick question. Clojure, yes. So it's all written in Clojure. This is an example of a macro. This is how we've extended the language. So in Clojure, there's no such thing as def project. There's nothing in the core of Clojure for a def project. And it's actually, somebody's written what we call a macro way to extend Clojure. So you don't have to write more complicated code. You're writing something that's a placeholder for more complex code or more involved code, and just giving it a name. So just like we've done with a function, we've given some behavior function. In a macro, we give a name to this code, and when Clojure looks at it, it expands it to something much greater. So here, basically, all we're doing is just defining a project, giving it a name, giving it a version, which just looks exactly like the same as a Maven version. And the most important thing is the dependencies. And what's the only dependency that we've got here? It's not difficult. It's not a trick question. I don't do trick questions. It is Clojure, yes. So I've got Clojure version 1.7. So I don't need to install anything. I don't need to install Clojure specifically. I'm installing the build tool called Leiningen to do that for me. And it basically just pulls down Clojure as a dependency like any other dependency. So you don't need to have like a 60, how big is Java now? Like 100 megabyte download. Hopefully Java 9 is going to be a lot smaller. But you can basically just download Clojure by creating a project. And if you don't have the right version, then Leiningen will pull that down for you. And you can do line depths will actually go off to Maven Central and something called Clojures and actually pull down any dependencies. I don't need to because I've already got it. But it would go and do all the whole Maven thing, pull all the dependencies down for me. So it's very simple to actually get going with Clojure. And then you just need a nice editor to edit in, preferably one that is Clojure aware, syntax aware, and gives you lots of all the auto-completion and things like that for the language. So let's look at some other examples. So you can call some simple functions. So what do you notice about this, apart from the brackets? If we're adding, what do you think this is going to do? Again, it's really obvious. It's going to add numbers together. But in Java, you would write, 1 plus 2 plus 3. This is getting a bit tedious. There we go. You'd write that. So you actually have infix order in Java, and in Clojure you have what we call prefix notation. So the function is the first thing, and everything else is the data. So plus is a function. It's not an operator like in Java. It's actually just a function like anything else. And we're giving it arguments. So we're giving the plus function arguments of 1, 2, 3, 4, 5, and off we go. So we can evaluate that. And we get 15. And the nice thing about having prefix notation is there's absolutely no ambiguity in what's going to be evaluated, how it's going to be evaluated. So you would go and start in the brackets in the middle there and evaluate that. And that value there would be times by 4. And then you would take that value and add it to 1, 2, the value of that, and then 5. So it can be a little bit weird at first to read it. So you sometimes start in the middle of Lisp, of Clojure, and then work your way out. But a lot of the things depends on how you actually write Clojure as well. And you can do some Java interop as well. So if I want to convert a string to uppercase, again, I haven't need to do anything else. I can just call the string static method to uppercase on a string. A string is a Java string, so it will just work straight away. I don't need to do anything complicated. I don't need to create any objects as well. I don't need to do string new my string string new or string my string equals new string and then the value. I don't need to write that. I can just actually create a string, and it's a lot more terse, and Clojure just knows what to do with it. And I can do all sorts of other things with Clojure. I can get all sorts of information out. Here I'm just using the system, get property things there, so I can find out what kind of environment I'm using. And I can combine that with, it's just like any other Clojure code, so I can use other Clojure functions with that as well. So I don't need to do anything complicated to do Java interop. And here I've got some functions that kind of get the project file and print it out for me. Here we're going to get the project file. We're going to slurp it in. It's a bit of a weird name, but it's basically pulling the file in, and then we're going to read the lines into a string, so it's not just characters. And then we're going to get the particular number in the index, because a string has an index, just like a vector. So we're going to get the element that's number 2. So as we know, when we're thinking of vectors, that's actually going to be the third element. So we actually get the third value out of my project file. Now that looks a bit tricky to read, so there is another way to actually write it. So you can reformat it, but you can actually use, again, another macro. So here we're kind of getting the project file. We're then going to pass it to slurp. The result of that then goes to read string as an argument, and the result of that then goes to nth, the result from the previous one, and then 2. So it looks a bit like, so if you imagine where these commas are, that's where the value from the previous function is going to end up. So it's going to end up as an argument to the next function. So it just makes it really, really easy. You can read it sequentially, even though it's still functional code. So it's a nice way to actually format the language and make sure you keep it nice and readable. And you can do other things as well. There's, so just to give you another example here. It's a very example to show it. So this is the threading macro in action. Oh, that's not quite right. So I want a string. I put there we go. And I can just change something and reevaluate it straight away. So it's very easy, very quick and simple. I mean, I don't need to go back and compile each time. I've got the REPL, I can explore the language and the code, and it's a really nice way to actually learn how to use Clojure, just because you can just type stuff in and see if it works. Because you can instantly get that feedback straight away. And if we want to speak like Yoda does, then we can use backward. This is we can actually use the threading macro that's got 2 arrowheads on, and this actually puts the result of the first function call as the last argument to the next function. So we can do all sorts of funky things like that as well. And it just makes the whole thing code a lot easier to actually read and work with. Okay. So let's just mention side effects. So print line does what you think it is. It actually prints a value. Oh, what value is it? What value has it given me? Nil. Yes, it says so at the end. It's a bit of a clue. Again, these are really obvious questions, sorry. The easiest ones are usually the hardest. But what's it done in the bottom? It's actually printed out the string in the bottom in my REPL, effectively my console log, my standard out. So it printed the value. So this is an example of a function affecting something else. So it's not just returning a value like all of the functions do. In this case, this is a kind of a naughty function because it's doing a side effect. It's actually changing something outside of itself. It's actually changing state in something else. In this case, it's changing state in our console log. So we try and avoid that, because what we want to do is actually just return the string. We could use functions like string, and there's a print function as well, which actually returns it. So when I call this, I get the value back again. It's not going somewhere else. And that's what you do with all the functions that are out there. And yeah, you can use string to join things together, and all sorts of stuff like that. Math, again, is really straightforward because it's all prefix. Oh, hang on. What's the result we've got there? It's different. It's not a decimal number. We haven't divided it. If we take, let's take another example. Let's just have 22 over 7, which is roughly pi. I didn't actually realize that was not actually pi until I started playing around with this. But there you go, you learn something every day. So instead of giving me 3.14 blah, 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 it's giving me 22 over 7. Why is that useful, do you think? Precision, yes. You're not losing. It's a really simple example of lazy evaluation, and a lot of Clojure is lazy. Doesn't mean it's like useless. Lazy in a good way. It means that you're only evaluating something when you really need to, when you actually need it, and because it's immutable, then you can kind of pass that around to lots of different functions, and they can interpret that. They can evaluate it in the way they want, to the precision they want. So you might just have one function that evaluates it to 3, another function that evaluates to 3.1, etc., etc. So each of those functions has the opportunity to use that information as it needs to. And it's a really nice way of doing things. If I do another example, 12 divided by 4, what do you think that's going to give? Oh, it is actually, isn't it? Yes, whoops. What was the example I was going to do? Oops, what did I do? No. Is it 30? I'm not sure. Yeah. So instead of 38 over 4, it's actually reduced it to the lowest possible fraction, as it were. And that way, you're kind of saving the space you're storing it in, but you're not losing any precision either. So let's have a look at other stuff. So we'll skip over that. There's a lot more examples I'm not going to get a chance to go through because I've got 3 minutes left, I think. I could talk all day about this. Yeah, I really could. I have done before. So you can create all the data structures very simply. You can use, if you want to create a list, you can use a list function, or you can actually just create a list like this. However, list is a special data structure. So if I do this, it's actually going to cause an error because what it's trying to do is trying to call this function, try to call 1 as a function, and I haven't defined 1. So what I can do is just use something called quote, and rather than actually write quote, which is a function, I can just use this shortcut, which is just the quote character. So if I evaluate that, then I get a string, I get a list returned. There we go. So it's simple. So it's really easy to define them, and vectors is the same. So you can use the vector function, or just use vector, and maps. So here's an example. Again, Star Wars seems to be a nice theme. So here we've got a map I'm going to evaluate. And the nice thing about maps is that if you use these, the blue words have got a semicolon in front, which means they're a keyword. It just means it's a name that points to itself. Rather than pointing to a different value, it actually points to itself. So you can it's like a little lookup. It's like having a geolocation tag in your code. You can always go to that point in your code just by using the name. So in this case, we've got our map called Star Wars characters, and we're going to get from the Star Wars characters Luke, the value for Luke. So if we evaluate that, we should get, we get Luke Skywalker. So we get, we get the value underneath Luke. So we get this map returned. And we can refine that as well. We can actually, because we're returning a map, we can then get the full name from that map as well. So we get Luke Skywalker. We can also write it in a slightly nicer way by using getIn. Or we can even do it the really cool way of using functions, using keywords as a function, and using the data structure as a function as well. So your data structures and your functions all have functional behavior, which makes it interesting at first, but it makes it really, really powerful as well. So it's very easy to get information out of a data structure and play around with them, experiment them. That's why these data structures are very, very important to when you're building an application. And I'm about out of time. There's tons more I'd like to show you, but what I can do is I've got a very nice little tutorial up on here. Well, there's a really nice one called Clojure for the Brave and the True. If you go to braveclojure.com, it's a really good tutorial. It does have emacs in there, but you don't have to use the emacs thing there. And I've also got a really nice, simple, introductory kind of build your own server-side web app tutorial. It's like step-by-step, walks you through there, even has all the code in GitHub, and covers a lot of the theory around how to build it's like a server-side application using Clojure. And yeah, that's it. And if you want to get some tools, there's a nice tool called Lighttable, which is a nice, simple tool. It's actually a Java environment, Java tool that's actually been written in Clojure. It's actually written in Clojure script, so it's actually running inside a browser, but you don't really notice that. And it's a really powerful way of learning, because as you're typing your Clojure, it's actually evaluating it character by character. So it's a really nice, simple way to learn, and it's nice and lightweight. Or you can also use Cursive, and you can jump into your IntelliJ and use it from there as well. So that's all I've got time for now. But thanks for listening, and I hope you really enjoyed it.